Hello, everyone. It's my pleasure to share recent work study state convergence of the continuous time routing system with the general distribution in heavy traffic. We consider a routing system with only one source of arrival, routing to unparalleled stations. For each station, we equip it with a single buffer and a single server. The service rate is mu1 for station 1, and the uh, arrival rate for this system is alpha. People often use the joint third queue policy, means that upon this job arrival, it must be routing to any one of the station, following uh, to find which one is the assorted queue length. This is have a very good advantage, including balance load, minimizing queue length and waiting times. It is also a very key component for some applications. It is very wide applied, including data center, parallel computing, and healthcare systems. Actually, in computer science, if the number of server stations is too large, if you check all of the information of the queue length of these N stations, it will be very have a very high cost. So they use the powerful two policy, means they only randomly choose any two of them, and then they just assign the job to the shorter queue length one. So this is very memory efficient and easy to implement. So a natural question is what's the station distribution of this continuous time routing system with general distributions? Actually, it is a very challenging problem because there's no explicit formula, especially for some Markov chain, including the continuous time but exponential distribution or discrete time with general distribution. So people often use the traditional heavy traffic regime, meaning that uh, you set this total arrival rate and the total service rate. The difference is very close. Will goes to zero means so that the utilization of this system will goes to one. In this traditional heavy traffic regime, we just set the number of stations is fixed. In this work, we prove the statistic convergence for the continuous time routing system with general distribution in heavy traffic, so that some non-exponential distribution are included, including gamma distribution, Pareto distribution, and log normal distribution. We only require very mild moment assumption for general distributions, so that it will be very friendly to heavy tail distributions. In this work, we utilize the proof tool based on joint relationship. This is very easy to implement so that we can easily extend the exponential distribution setting to general distribution setting. This is our main result. We assume the interval time and service time have only finite 2 plus deltas moment. So under this policy, we can have this result so that the skewed statistic equivalence vector will convert to the same exponential random variable. Actually, uh, this this is called state space collapse because all the components convert to the same random variable. Uh, we have some literature about this statistic collapse. In the initial, people focus on the process level statistic collapse, meaning in the finite time horizon, we have this result. But later, people focus on the steady state SSC. First work is derived by drift method. They prove the moment SSC, and later people use the variant of the drift method is called transform method to get the distributional SSC. And people can use the stance method to get the conversion rate of this SSC. However, all of them focus on the Markov chain. In our work, we focus on Markov process. This is the main difference. Thank you very much for your attention.